Okay. Should I get going? All right. So, yeah, thanks, Anne. So, hi, everyone. I'm Josh. I'm at the University of Toronto. I do astrostatistics, which means I'm sort of half in statistical sciences and half in astronomy and astrophysics. Well, technically 51% in stats because somebody has to be in charge. So I'll be talking about some very recent work. So originally, I think the idea when Anne invited me to talk was that I could talk about some of the problems in astronomy. We could do some stars, be a good contrast to the stuff that Rachel will talk about sort of afterwards. And then about 2 weeks beforehand, I'm like, could I just instead present on this idea, which I ran, and I'll prove it mostly in the last couple, essentially in the last 2 weeks or so. So you can see here, so Claude essentially wrote 30,000 lines of code, and you'll get to see how it did. I also want to fully acknowledge that it also made the slides. So I have a little thing over here just highlighting my attribution statement. So I tried my best to get it to stop doing some of the AI isms, but I apologize if you're I've seen enough of these, not this, but this. Anyway, let me know. So this is work that I've done with James, Ricardo, and Anne, essentially trying to do this, again, continue this tradition that we've seen earlier, sort of at the workshop about sort of this frequentist Bayesian sort of concordance, or as we might call Frasian inference. I think Larry coined the term. Trying to kind of have our cake and eat it too. So what's the fundamental challenge? Is that in astronomy, we have all these different data sets. I work a lot with stars and galaxies. This is just some mock data sort of showing some correlations between the mass of a galaxy, which is on the y-axis, and the rate at which it forms stars on the x-axis. And there's some correlation between these two things. Stars that are bigger galaxies that are bigger tend to also be forming more stars. So they're sort of assembling at some rate. But the weird objects are always the ones that are most interesting because they have some really weird evolutionary pathway. There's lots of different history that's behind them. You often want to identify these types of quenched galaxies or post-starburst galaxies because there's often something really interesting going on. You can do lots of physics and detailed follow-up. The problem is that, of course, when you're running sort of some generic framework over it, these are often the things that are 5 sigma outliers, or they're definitely do not agree with the prior. And so you get this standard result where you get this prior shrinkage. And so you end up with an estimator of its properties that are both really biased and overconfident. And often what people do is they'll first sort of comb through the data, trying to find these things by eye. And then when they find some of them, they will then rerun with a new set of priors, often designed to be much more expansive or bespoke, or they'll sort of tune lots of the priors adaptively until they get something that kind of they feel like is a better match to the data. This is definitely not what you'd call standard Bayesian inference, right? There's sort of some neural model selection, being like our brain this time, being done by eye, trying to get all this to work. And then in the end, you end up with some results. And this is pretty common in lots of different areas. So you could say, okay, but why would you do this? You can just use frequentist methods, then you're guaranteed coverage, right? But this also makes you lose a lot of power in the regimes where you have a lot of galaxies in the prior. Most of the time, your distribution does in fact follow something that's relatively close to the prior. That's often where we've derived them. And so you end up with this trade-off where, yes, you can maintain some coverage and kind of capture these objects if you just do frequentist-based inference, or if you do Bayes, you do really well on lots of objects, but then you kind of fail for these types of outliers. So I started thinking okay, can we kind of have our cake and eat it too? And this is when I started working a little bit with Anne and James and other people as part of the SAMS team. So I've already seen tons of these plots before. They're much better than this one, which Claude made. But this is the idea is you can say, great, what we can do is we can actually incorporate the prior into the test statistic and then do this Neyman-Pearson inversion to then get sort of these confidence intervals, which you can then combine to form different types of sets. And so you can then use a statistic that picks the prior. So you're incorporating the prior while still guaranteeing frequentist coverage. Seems okay, but you don't get anything for free. So the problem is that if you do this type of thing, so this is an example using Waldo, which was first, I think, published. Well, there's a long history of people doing this type of thing, but I think this particular formalism was from Luca, who worked with Anne a few years ago. where you just essentially have replaced, your mean and variance with just that from the posterior instead of from the likelihood. So this is a p-value function. So the idea is that you're sort of looking as a function of the parameter. You get to compute this test statistic, and that gives you a p-value. And then you draw a line essentially based on your confidence interval, and that sort of slices into your given region. So this is sort of what this looks like for this particular posterior-based test statistic. And so what happens is that this is, again, with prior data conflict. And so you don't get anything for free. And so you don't have an overconfident sort of biased estimator, but you have to compensate by really drawing out your interval to make sure you capture all of that space. So as the data conflict with the prior becomes larger and larger, you sort of need to drag your interval ever more sort of back into the prior in order to correctly capture lots of the correct distribution and maintain coverage. So this is okay, but seems like something where you could maybe try and clean up. One thing that will help here that I'll reference is this idea of a confidence distribution where you can combine lots of these different intervals together. So you imagine you can just slice this p-value function at lots of different level sets. And then if you took all those things together and then kind of turn them into a density, you get something that looks like this. And so this is kind of an equivalent object you can think of like your posterior, where now this thing, if you look at the CDF and you construct sets from it, kind of gives you correct coverage in a frequentist sense. So this kind of is what we have. So there's nice literature here, and eventually I need to definitely read a lot more on this because I'm a very new entrant on the stats side. So you end up with this bias where you have to correct essentially as the prior data disagreement becomes larger, your interval becomes more skewed, it becomes much bigger. So you don't get anything for free. This is just another way of looking at this. So this is like a tax that you pay. So this is now looking at overall width of the interval on the y-axis and the true parameter on the x-axis. So the thing that you are actually testing against. This shows the size of the interval at that position. And of course, if you agree with the prior, then you have a more powerful test. This is a lot like, the focus function in higher energy physics that was presented yesterday. This type of thing is exactly what you want. So if you have really good agreement with your prior, you do better. But of course, if you're really far away, the turnover happens around like 2 to 3 sigma, you do much, much worse. And the amount, of course, depends on how strong your prior is, right? If you have a stronger prior, then the disagreement happens sooner. This is in the normal case, which will be what we focus on for most of the talk. So I had this idea where I said, look, in practice, right? If you give someone a measurement that's 5 sigma off, an astronomer will say like, well, I don't believe this. I'm just going to rerun this with a new prior. And usually what they'll do is they'll make it a flat prior because that's uninformative, right? So they'll just rerun it with a flat prior and they'll say, great, this is what I do. So there's been some weird sense in which you've done like a hypothesis test and then model selection. You've chosen this other model that has a much broader prior set so that the likelihood can sort of dominate in the inference. So I thought, like, is there a way that we can try and take this into account when we construct these types of Frasian inference procedures? So I looked at sort of the literature on tilting, the idea that you want some sort of family of functions or some mapping that can take you from the posterior on one end to the likelihood on the other end. So that's the basic idea. The most sort of natural way of thinking about this, at least to start, is that you can just take the prior and raise it to some power. And so if it's raised to the power of 1, you get the posterior. If it's raised to 0, you get the likelihood back. So this gives you a little family of possible distributions. And we'll get back to different ways that we might select this. But more importantly, the idea is that you're also modifying your test statistic. So the idea is that based on where you're testing, so if you're testing something that you think is close to the prior or something that's far away from the prior, your test statistic might actually change. So you'll sort of convert from a posterior-based thing to a likelihood-based thing. So I thought, oh man, this is going to be great. Now we can have our cake and eat it too. If we're 10 sigma away, we should always regress to testing against walls and doing a likelihood test. If we're really close, we should use the posterior. That's going to give us sort of maximum power. And now we don't have to worry about this. So in theory, this is what we would do. So the idea is that if you see something at, say, 2.5 sigma, you can then find sort of under which sort of set of tilting you have, what gives you the smallest sort of confidence interval. In this case, that would be just using the likelihood. And then you would just pick that value at that position and you could call it a day. So I learned very quickly that this doesn't work. This is cheating because, of course, you've seen the data, right? So if you see the data and then you pick the value after seeing the data, you undercover because you're overconfident. So I ran some tests, and indeed this was true. On average, I undercover in this case by about 3%, and I was very sad. So I realized this is a common thing that I learned for post-selection inference because you're looking at the data. So I realized, okay, what I should have actually done was I should say you should actually be selecting based on the value that you're testing, not the value that you see with the data. So this needs to be data independent. So the idea is if I'm testing a value that's 5 sigma away in theta space, I should have that value picked independently. And then what I do is that at that particular value, my test statistic will be with some tilted distribution. So it'll have some value. So the p-value function will have some value that I can evaluate. I can use that to construct a confidence distribution. And there we go. So the idea is that now, this is what's shown on this plot. You can define some function. This is the one that I started with that seemed very natural. That's sort of, if you're testing a value close to the posterior center and the prior, you should really believe the prior. You should be very posterior dominated. As you go really far away, you then want to revert back to the likelihood. So I said, this seems very reasonable. And then for every single value here, you can essentially draw a line that says, okay, based on this, I'm going to have some different test statistic. I'll get some different p-value. Then I can sort of turn all of this into some new p-value function that turns into some distribution. So that's sort of what this shows, is that under different versions of data prior conflict, you end up with these new types of functions, which now have this dynamic adjustment. So as you're far away, you're sort of likelihood based. If you're close, you're posterior based. This is the basic idea. So I thought, okay, great. This potentially allows us to adapt to this, but we've done it before. Now, in a Bayesian setting, we might say that this would just be equivalent to having some meta belief about the prior. And we could solve this by having a hierarchical model where our prior hyperparameters maybe depend on where things are, and we sort of parameterize it using a certain way. But I thought this potentially kind of splits the difference by always guaranteeing some coverage, but also allowing us to adjust our prior belief dynamically, but never cheating, right? Always based on some tests that we're doing. Okay, so I thought this is great. Then immediate first problem is this can cause very odd behavior. I apologize, by the way, for this overload in the captions. Claude did not catch this when it was making the plot, but essentially the idea is that you can have this very weird behavior where you get two separate confidence intervals that can come out. The reason is that, again, if you're testing close to the prior and you are very confident because you're close to the prior that you should have a lot of power, so you sort of boost your p-values in that region. And so as you think you're close to the prior and you're testing, you get this big spike. Then as you go away, you sort of are decreasing. You believe the prior less and less. And so if you have a big data conflict over here, eventually you get closer to the data, you then believe yourself again, and then you go back up and you come back down again. So this gives you these sort of weird 2 different intervals here. So for all the tests, what I'll just say is that I do actually keep track of these regions separately. I have a sort of root finding approach I use to identify both of these rather than using the convex hull. So all the results are showing what I would call the most fair representation, which is really the total join size of these intervals, not the hull that spans both of them. So now, okay, what about tilting, right? So the idea is how do we find a pathway from the posterior to the likelihood? So I talked about this power law method. So this is also called the E geodesic. And you can think of this as just direct linear interpolation in log space, right? You're raising stuff to a power. So in log, this is sort of something 1 minus eta times log pi plus log likelihood. You can also do just a mixture. This is called the M geodesic, which is just directly adding this together in linear space. So you just have one distribution that's just the posterior and one that's the likelihood, and you just have a weight between the two of them. So this can cause very weird things. In this case, it is just a mixture of Gaussians, but I will include what this looks like in a sec. Then there are 2 other ones I want to test. There's this nice Fisher-Rao geodesic. So you can think of this as just moving along this metric. And this kind of does some really fun stuff for the Gaussian, which I'll show. And then you can imagine an optimal transport style approach where you essentially are saying I have these 2 quantile functions, and I want to linearly interpolate between all the quantiles at every given position. And so this is sort of in this Wasserstein style metric, W2. So I tried implementing both of these. You get nice analytic solutions if you're doing this for Gaussians. So that's what's shown here. So this is showing the mean on the x-axis and the standard deviation on the y-axis. And in this case, again, sort of in the normal case, you end up with extremely similar pathways for the power law versus optimal transport, although the rate at which you proceed along those pathways differ a little bit. You can see this fun little arc that comes from the Fisher-Rao, where you sort of are changing the standard deviation along with the mean in sort of this kind of cycloid way. And then, of course, the mixture model is the one that has the largest possible change because you're adding on the second Gaussian component, so the variance like really blows up. So, okay. So the idea is that there's some optimal like distribution here that we might want to explore, which of these kind of works well. I'll skip a lot of the exact results and say that in general, I'm just going to focus on the power law and the optimal transport, since the other two at least are sort of suboptimal for the normal case. Okay, so then the question is, how do we optimize this objective? So I have some function, right? Some eta, some tilting that I want to change depending on where I am in the space. Like how much do I believe my prior based on what test I want to do? So how am I going to adjust my belief dynamically? So one way to do it would be you'd say, I want to kind of maximize my power. So I want over some calibration range. So again, you make some choices about over what range you'd like to have statistical power and what distribution you'd like to assume. So I'm just going to assume sort of flat, sort of plus minus 5 sigma, which I feel like is pretty reasonable, but you can pick whatever one you want. One thing that I originally targeted was I said, I just want to have the smallest possible width. So that's the most power. You want to have the smallest confidence interval width over some fixed alpha. Then I said, well, why can't I just have the smallest width averaged over all of the alphas, right, over every possible range? And it turns out there's this very nice trick where if you try and say, I kind of want to minimize the width at all possible alpha levels, which is this red thing, that's sort of like doing this Lebesgue style slicing integration. So you can swap variables, and then you can actually just do this in the y-axis, which is in the p-values. So this ends up being equivalent to integrating over the p-values over the parameter space, which was a fun thing I did not know. So that was very cool. So in addition to this, I also tried one where you actually also can minimize the variance of the confidence distribution that's constructed from this as well. They kind of give similar results, so I'm just going to compare both of these in the plot on the next slide. So idea being minimum sort of average width of these confidence intervals over all of the parameter space versus the sort of variance of the distribution you construct using all of these different intervals as well. Now, how would you do it? Here's the second use of neural, except this time it's the neural network and not the neural brain. So I said, okay, great. I need to have some function. I want it to be flexible. I'm just going to parameterize this with a neural network. I just use a very small GLU MLP, like 128, 128, 128. And then I condition this based on values for the prior and then values for the likelihood, because I wanted to amortize over possible different disagreements between the data and the prior. I also add on the second thing. I want it, in theory, depending on the metric, you actually can extend beyond 0, 1. So you can over sharpen or sort of under sharpen in some cases because you have some metric or linear thing. So I just wanted to see whether you could learn things that would go, say, beyond 0 and 1. So I also trained a second neural network that sort of allowed us to learn this as well, which sort of what thetas are admissible in this case. Okay, so that's all of it. I was very excited. So I said, what do we get? And the answer is it's flat. So it was, I tried really hard. And at least for this very basic problem, what happens is that each of these lines is highlighting a different sort of like a sigma level for the prior. And so based on how strong your prior is over a fixed parameter range, you do end up adjusting your level of belief to sort of maximize power, sort of minimize the size of your intervals. The exact range depends on exactly how quickly you move. So for power law and for optimal transport, you have different sort of rungs. This is also slightly different if you're maximizing or minimizing the variance of the confidence distribution versus just the integrated p-values or the sort of average confidence interval size. So they look a little different, but the overall result is the same. And it just turns out that in general, what happens in practice is that this curve I showed you originally, where you really if you're close to the prior, you super believe it. And if you're far away, you don't. That has a huge cost. Essentially, because you always believe the prior when you're testing close to it, no matter how much data prior conflict you have, you always end up really pulling yourself back towards the prior. And so that actually leads to this fundamental problem where this local, really strong prior belief will actually lead to a global reduction in power because the intervals just get too big. So that's what's shown here. So the default Wald and Waldo is this gray and black line. So in general, if you're far away, and again, I trained this over -5 to 5, you'll do worse over here, and that always is more of a penalty. If you do this optimal sort of pick your value and then only choose that value, that would be this red curve. That's the one where you're sort of more confident near the prior and less confident far away from the prior in terms of how much you believe it. If you take the function that would give you this red curve, which is wrong, and then you do the correct procedure, which is applying it over all thetas, you get this blue curve, which is way worse. So in this case, what's happening again is that you sort of believe the prior way too much, and that really penalizes you far away from the prior, even though you don't want it to. So the green ends up actually being a really good trade-off. You sort of really try and, you still do much better when you're close to the center because the prior helps you. When you're far away, just the slope is much reduced. So that was kind of a result that was less exciting, but, made some sense after I thought about it for a while and then tried to fix it for, 2 days. Okay. So anyway, I thought this was kind of a fun, thing to highlight. So I'll just try and step back and summarize. So basic idea is that in practice, what happens in a lot of astronomy and astrophysics and the problems I work on are that people are always interested in these sort of outlier rare objects. And so they want to identify them. But if you're in a Bayesian framework, it's exactly these objects which you're super penalized against. And so people do all sorts of strategies to try and identify them. And then they will rerun them with a bunch of different models that they think work better, but without any sort of tools for selecting them. And so I thought, hey, maybe I can come up with a procedure that kind of is well suited for identifying these rare objects, maintaining coverage, but maybe doesn't require us to, have to rerun things or penalize stuff a bunch. So what we looked at was allowing this tilting essentially between your belief in the prior, at some position in parameter space, adjusting from full belief to some partial belief. And then once you have a proper procedure for inference and you can create these confidence distributions, the end result ends up being that depending on how large of a calibration region you want to have good behavior in, you sort of decrease your belief by some amount, depending on how strong your prior is. And in general, that seems to work pretty well. I'd be really interested in applying this to sort of normal cases, especially where you have much more complicated distributions and you have to solve things more numerically, which is on the to-do list. And then also seeing how this works in a couple of different cases. James has talked about, SPI under some misspecification. Josh Ingram has talked about this as well and had a poster earlier. And I would love to see extensions of this into a couple of multidimensional cases and potentially using this as a way of dealing with out-of-distribution data. So I thought this was a fun potential extension on this approach of thinking about how you can, sort of adjust your prior belief based on what you're testing. It, didn't work as well as I thought, but I still thought it was ended up as a fun project. So yeah, happy to take questions.